All right, let's pull back the curtain on something that pretty much runs the internet, the relational database. You've probably heard the term, but today we're going to break down what it really is.
Think about it for a second. How does Instagram remember every single photo you've ever posted? Or how does Amazon know every single thing you've ever bought? I mean, all that data, your profile, your friends, your shopping cart, it has to go somewhere, right? It can't just be floating around out there in the ether. It needs a home. It needs a system.
So let's talk about that system. The best way to picture it is as a gigantic, incredibly well-organized digital filing cabinet. Seriously, this is the big idea behind relational databases, and honestly, it's the only thing stopping the entire internet from being a complete and utter mess. Okay, so the official name for this is a Relational Database Management System, or RDBMS for short. And the key word there is relational. Everything is designed to be connected. This is not your digital junk drawer where you just throw stuff in. No. This is a superstructured cabinet where every single piece of information has a specific place, making it easy to find, easy to change, and, this is the most important part, easy to see how it all relates to everything else. All right, let's make this real. See this? This table here is just like a drawer in our filing cabinet. We'll call this one Users. Now the columns, you see user ID, name, and email, those are like the pre-printed labels on every single folder inside that drawer. And each row, well, that's a single folder for a single person. See how neat that is? Everything in its place. Okay, so we've got this amazing digital filing cabinet. But how do we actually use it? I mean, you can't just go in there and start pulling out files yourself. That would be chaos. Nope, you need to talk to the librarian. A super smart, super fast expert who knows this system like the back of their hand. And this librarian, they speak a very specific language. It's called Structured Query Language, or as you'll always hear it, SQL, sometimes SQL. This is the one universal language for talking to pretty much any relational database on the planet. If you want to ask a question, add new information, or change something, you speak to the database using SQL. Now, SQL isn't just one giant thing. It's kind of got different dialects for different jobs. You've got DDL, the data definition language, which is what you use to actually build the filing cabinet, to create the drawers and define what the folders look like. Then you've got DQL, the data query language, which is for asking questions, like selecting some data. And then there's DML, the data manipulation language, for actually changing what's inside the folders, like inserting new info or updating old stuff.
And look at this, a real SQL command. It looks a little technical, but it's actually just plain English. This is literally you telling the librarian, hey, select the name and the email from the user's drawer for the person where their user ID is 12. Boom. It's super specific, super clear, no confusion. You get exactly what you asked for.
So having a structure is awesome, but to make this system truly powerful, you need some rules. You need a way to keep this whole filing cabinet from getting messy and filled with the same information over and over again. Just imagine this for a second. Let's say you have a customer and they place 100 different orders. Are you really going to write out their full name and address on every single one of those 100 forms? No way. It's a total waste of time and space. And what happens when they move? You'd have to track down all 100 forms just to update their address. It would be an absolute nightmare. And this is exactly the problem that normalization is designed to solve. It's basically a set of rules for organizing our database to get rid of that repetition. The main idea is super simple, but incredibly powerful. You store each piece of information in exactly one place. That's it. The customer's address, it exists in one spot, period. Check out this before and after. On the left, before, you've got this one big, messy table where the user's name and address is repeated for every single order. But on the right, after, it's so much cleaner. We've split it into two drawers, one for users and one for orders. Now the user's info is only in one place. If they move, you change it in that one spot, and you're done. So much better. Okay, but wait, if the order info is in one drawer and the user info is in another, how do we link them together? How do we know which order belongs to which person? Well, that's where keys come in. The first thing we do is give every single folder, every row, its own unique serial number. We call this the primary key. It's like a social security number for that piece of data. No two rows in the same table can have the same one. And this is the secret sauce, the foreign key. So back in our orders drawer, instead of writing out the whole user address, we just jot down their unique primary key. So the order form might just have a little user ID 12 on it. That's the foreign key. It's basically a little sticky note that points to the other drawer saying, hey, for all the details on this customer, go look at folder number 12 in the users drawer. And that's it. That's how we create those powerful relationships.
Okay, so normalization sounds perfect, right? It's clean, it's efficient, it makes sure our data is accurate. What's not to love? Well, there's a catch, because sometimes being perfectly organized isn't actually the fastest.
Think about our librarian again. Let's say you ask for a list of all recent orders and you want the customer's name on that list. With our super organized system, the librarian has to go to the orders drawer, grab an order, look at the user ID, then run all the way over to the users drawer to find the matching name, then run back. Now imagine doing that 1,000,000 times a second. All that running back and forth, in the database world, we call that a join. It can get really, really slow.
And that brings us to a concept that sounds a little crazy at first, denormalization. This is where we look at our beautiful, perfect system, and we intentionally break the rules. We decide, for the sake of speed, to add some of that repetitive data back in. So maybe we do put the customer's name right on the order form, just so our librarian doesn't have to run to the other drawer. It's a trade-off, all for performance. So really, it all boils down to this fundamental trade-off. Normalization is all about data integrity. It's fantastic for applications where you're constantly writing new data, like a banking app, and you absolutely cannot have errors. Denormalization, on the other hand, is all about raw read speed. It's perfect for something like a blog or a news site where millions of people are reading the same information and you need to serve it up as fast as possible.
So all this stuff, tables, SQL, the push and pull between normalization and denormalization, this isn't just theory. This is the invisible architecture, the foundation holding up practically every app and website you use every single day. And really, that's the big takeaway here. So much of building modern software is just this constant balancing act. It's a tug-of-war between perfect, pristine organization on one side and pure, raw speed on the other. Engineers have to make these tough calls all the time. Do we make it safe or do we make it fast? And the answer is usually, it depends. So this structured, rule-based world of the relational database gives us amazing reliability. It's a rock-solid foundation. But it has its limits. So what happens when your data is just too messy to fit into neat little tables and rows? Or what do you do when you need to scale to a size that's just astronomical? What happens when you need to ditch the file and cabinet metaphor altogether? Well, that's a whole other can of worms, and a story for another explainer. Thanks for joining me.